Moving on to the excitation and inhibition process. In this presentation, I will discuss what happens in the dendrites and soma of the neuron that leads to the firing of that neuron. First, recall that a neuron is at resting potential until it receives enough chemical messengers to reach threshold. Once threshold is achieved, the neuron will fire its action potential. Also recall that in this example, we're only dealing with neuron-to-neuron communication. We'll address external or sensory stimuli in the sensation and perception unit. So here we have my poorly drawn image of a neuron with its four primary parts labeled. The dendrites, which receive the chemical messengers from other neurons. The cell body or soma, which maintains the vital functions of the neuron. The axon hillock, where the integration of incoming messages takes place, and the axon, which sends a signal down its length to release chemical messengers to other neurons. The neuron in this drawing is also shown to make a connection with the dendrites of another neuron. This connection is called a synapse and is shown in more detail later. You can see that this neuron has made several synaptic connections, either with one other receiving neuron or potentially with many. In this even worse drawing, we can see that neuron A is releasing its neurotransmitter into the gap between its axonal ending and the dendrite of neuron B. So I'll first describe the process of excitation. Therefore, this neurotransmitter is likely to be glutamate, which is the most common excitatory neurotransmitter in the brain. The vesicles in the terminal button are first pushed up against the cell membrane and then open to release the neurotransmitter. Glutamate molecules will then move across the tiny gap between the point of their release from the axonal ending of neuron A and the dendrite of neuron B. Receptors for the neurotransmitter are shown on the dendrite. These receptors will only bind, that is, pick up, molecules of a certain shape, in this case, that of the glutamate molecule. These receptors are connected to another type of channel, which are called neurotransmitter-gated channels. In essence, these channels can be thought of as doors that open when they are unlocked by the key, that is, the glutamate molecule. Sodium, as we said, carries a positive charge, adding positivity to the negative 70 millivolt charge within the neuron. This drives the voltage within the neuron to, let's say, negative 67 millivolts. This driving of the internal voltage closer to zero is called depolarization, and it serves to excite the neuron just a tiny bit. We call these small positive charges created by the entering sodium ions excitatory postsynaptic potentials, or EPSPs. If the neuron is depolarized enough such that the threshold value of negative 65 millivolts is achieved, a major event will occur and the neuron will fire an action potential, which is basically a spark of electricity that travels down the length of the axon and causes the release of that neuron's own neurotransmitter. If the sodium channels are opened several times, EPSPs travel the distance to the axon hillock such that sufficient depolarization occurs there to reach that threshold value. However, this opening of the same set of sodium channels must be done in rapid succession. This is a process that we call temporal summation. A neuron could be excited by glutamate or any other excitatory neurotransmitter at several different synaptic connections. The adding together of all of these inputs across the entire space of the neuron is called spatial summation. It's important to note that in order for an action potential or firing of the neuron to actually take place, the threshold value of negative 65 millivolts has to occur at the axon hillock, which is where the action potential is initiated. The inrushing sodium ions do not change the voltage value for the entire neuron, just only at that location. That local excitation must travel all the way to the axon hillock in order to fire the action potential. Not all synapses involve the excitatory neurotransmitter glutamate. By some estimates, up to 80% of the synapses in the brain do not involve excitation at all, but serve instead to inhibit neurons. The most common inhibitory neurotransmitter is gamma-aminobutyric acid, or GABA for short. GABA is released by axonal endings in the same way that glutamate is released. And GABA also traverses the synaptic gap and binds to receptors on the dendrites. GABA also fits into these receptors like a key in a lock and opens neurotransmitter-gated channels. However, instead of opening sodium channels, GABA opens either chloride channels, allowing negatively charged chloride in, or potassium channels, allowing the potassium out. So from our discussion of resting potential, we know that the net effect of the forces working on the potassium ions is to push them out of the neuron. The result is to make the negative 70 millivolt potential inside the neuron even more negative. So maybe negative 72, negative 75, or even negative 80 millivolts. This process pushes the neuron's voltage level further away from threshold of negative 65. Therefore, more excitation is now required to fire an action potential. The greater the inflow of potassium ions, the greater the outflow of potassium ions, the more inhibition, and with it, the decreased likelihood that the neuron will fire. This outflow of potassium ions creates what we call an inhibitory postsynaptic potential, or IPSP. The inside of the neuron is pushed away from its threshold. That is, it's hyperpolarized. With something like 10 to 100 billion neurons in the brain, it's quite likely that at any given moment, a neuron is receiving information, meaning neurotransmitters, from several other neurons. Some of this information will be excitatory in the form of glutamate, which will allow positive sodium to enter the cell, and some inhibitory in the form of GABA, which allows potassium out and chloride in. If the net voltage, the sum of all the resultant EPSPs and IPSPs, reaches negative 65 millivolt threshold, the neuron will fire an action potential. But it's important to remember that this threshold voltage cannot occur just anywhere in the neuron. It must occur at the axon hillock. In other words, it is at the axon hillock where the integration of input takes place. It's as if there's a little man with a calculator sitting in the axon hillock adding up all the EPSPs and subtracting all the IPSPs. If and when this calculator reaches negative 65, the little man presses a button that starts a cascade of events that results in an action potential. How that action potential occurs will be the subject of the next video.